Whew. All right, let's take a look at some quick problems here to help us better understand some of the information in our content objective for today. Problems 1 through 3 here. One sort of giant problem says sodium hydroxide reacts with phosphoric acid to give sodium phosphate and water. If 17.80 grams of sodium hydroxide is mixed with 15.40 grams of phosphoric acid, number 1, how many grams of sodium phosphate can be formed? Number 2, how many grams of excess reactant remain unreacted? Number 3, if the actual yield of sodium phosphate was 15.00 grams, what was the percent yield of sodium phosphate? So just a couple things to keep in mind here. Anytime in a problem you are given two amounts of reactants, you are probably looking at a limiting reactant problem. So just keep that in mind as we move forward. Before we can even begin this problem, though, we are looking at a problem without a balanced chemical equation, which is sort of like a life without rain. So let's take a quick look here at how we can come up with a balanced chemical equation before we move forward. We've got our sodium hydroxide reacting with our phosphoric acid to yield our sodium phosphate and water. So this is a neutralization reaction. So we've got our base, we've got our acid. This is clearly an acid-base neutralization reaction. We're making some salt and water. As we look before moving forward, though, we need to make sure we've got this balanced. As you think about where to start, let's start with our metals. I'll balance the sodium first by putting a coefficient of 3 here. That'll balance my sodium. My phosphates, PO4s, are already balanced. As I look to balance my hydrogen or my oxygen next, I'm going to go to oxygen because I got my hydrogen in 2 places here. So I've got 3 oxygen on the reactant side, only 1 on the product side. So I'm going to put a 3 here. Of course, not counting the ones on the phosphate, but that'll balance my oxygens, and in so doing, it actually also balances my hydrogen. So how nice is that? Our coefficients here are then 3, 1, 1, and 3. Not necessary that you write in the ones. I just like to, helps me keep things on the up and up. All right, now let's tackle this problem. Number 1 says how many grams of sodium phosphate can be formed. Again, this is a limiting reactant problem. I've got 2 amounts of my reactants. And so I'm essentially going to do 2 different stoichiometry problems here to figure out which of those 2 reactants is going to limit how much product can be formed. So I'm going to start with the given amount of sodium hydroxide, and I've got that 17.80 grams of sodium hydroxide. And I'm going to work this through just to figure out how many grams of sodium phosphate I could make if I had as much phosphoric acid as I needed. So I'm going to go grams of sodium hydroxide to moles of sodium hydroxide. Again, that's my key player there, the mole. Once I get to moles of sodium hydroxide, I can compare it to moles of my sodium phosphate. And then I can go from moles of sodium phosphate to grams of sodium phosphate. As I look at some of the relationships here, 1 mole of sodium hydroxide relates to 40.00 grams of sodium hydroxide. Again, that relationship comes from the periodic table. When I've got moles to moles here, that relationship comes from the balanced chemical equation. So for every 3 moles of sodium hydroxide, I'm going to make 1 mole of sodium phosphate. And then again, another mole to gram relationship. That's going to again come from the periodic table. 1 mole of sodium phosphate has a mass of 163.94 grams. Quick calculator moment here will give me a mass of 24.32 grams of sodium phosphate produced. And that's assuming that I had as much phosphoric acid as I wanted to react all of my 17.80 grams. But what I'm going to do here is I'm going to do the exact same calculation, but this time with the phosphoric acid amount. So I've got 15.40 grams of my phosphoric acid, and I'm going to run it through just like I did with the sodium hydroxide to see how much sodium phosphate I could make. So we're going to go from grams to moles of phosphoric acid, and then from moles of phosphoric acid we can go to moles of sodium phosphate, and then finally from moles of sodium phosphate we convert to grams of sodium phosphate. Again, my relationships here, when it's grams to moles, comes from the periodic table. Phosphoric acid has a molar mass of 98.00 grams per mole. Our relationship here is a 1-to-1 relationship. So again, it's a different reactant. So our relationship there is a little bit different. Moles to grams comes from the periodic table. Again, that 163.94 grams per mole of sodium phosphate is the relationship there. Bust out your calculator, solve this. You end up with 25.76 grams of Na3PO4. Okay, so why did we just do that? Again, go back to the idea of the cheese slices and the bread slices making cheese sandwiches. Just because you have certain amounts of each of your reactants doesn't mean that you're going to use both of them completely up. And so as you look at these two dimensional analysis calculations, you want to look for the amount in which you produce the smaller amount of product. That will indicate for you then which of your reactants is limiting. So in fact, the sodium hydroxide is limiting. So I'm going to do one of these. Boop. Limiting reactant. Because we make less product. Boom. So again, as you're looking to determine which reactant is going to limit the amount of product you can make, you just need to do two quick stoichiometry calculations. Whichever one of those calculations produces the smaller amount of product will determine which of your reactants is going to limit the reaction. All right, so once we've identified sodium hydroxide as our limiting reactant, that tells us then that the 24.32 grams is the amount of sodium phosphate that can be formed, and is therefore answer to question number 1. Our next question asks us how many grams of the excess reactant remain unreacted. Okay, so to solve question number 2 then, we're just going to take our limiting reactant, the 17.80 grams of sodium hydroxide, and determine how much of the excess reactant we used. So we're going to go from grams of sodium hydroxide to moles of sodium hydroxide. And then from moles of sodium hydroxide to moles of our other reactant, our excess reactant, which in this case is the phosphoric acid. And then from moles of phosphoric acid, we'll go to grams of phosphoric acid. Some quick numbers here to plug into our conversion factors. Again, 1 mole of sodium hydroxide is 40 grams. This relationship here comes from the balanced chemical equation. For every 1 mole of phosphoric acid, we need 3 moles of sodium hydroxide. And then the molar mass of phosphoric acid is 98.00 grams. We bust this into our calculator to get 14.54 grams of phosphoric acid. Now, this is the amount of phosphoric acid that was used when I reacted that 17.80 grams of sodium hydroxide. Question number 2 is asking us how much of the excess reactant remains unreacted. So, if we originally had 15.40 grams of the phosphoric acid, and we're only reacting 14.54 grams of it, then we're going to have 0.86 grams of the phosphoric acid left over. Boom. And then finally here, question 3 says, if the actual yield of sodium phosphate was 15 grams, what is the percent yield of sodium phosphate? Well, to solve this one, as we take a look at some of the stoichiometry work we did earlier in the problem, if we started with 17.80 grams, in theory, according to our math here, we should get 24.32 grams of sodium phosphate. The problem is telling us, though, that in the lab we actually only get 15 grams, so we're not going to be at quite 100% yield. Let me give us a little more room here so that we can answer this problem or work through this problem. So percent yield is actual over theoretical times 100. Our actual yield, according to the problem, was 15.00 grams. In theory, we should have gotten 24.32. We multiply that by 100. Our percent yield here is going to be approximately 61.68%. So in reality, we're only expecting about 2/3 of what we should be able to get theoretically.